What's up, everybody? It's Miles here from bootcamp.com, and today in pulmonology, we're going to be going over pulmonary function testing. So recall from previous videos that we talked about an instrument called a spirometer. It's a machine that you blow into and it will measure different lung volumes, and you can generate different graphs based off that data. And so today we're going to be generating a graph that measures airflow over time. So on the slide, we have the skeleton for what the graph is going to look like. On the y-axis, we're going to have volume expired in liters, and on the x-axis, we're going to have time in seconds. The volume expired is going to be increasing in this direction, and the time in seconds is going to be moving in this direction. And as a result, as we expire more volume over time, our curve is going to be looking something like this. All right, so let's just add in our normal curve here. And there are 2 points on the curve that you really want to pay attention to. The first is going to be the forced expiratory volume in 1 second, also called FEV1. And the second is called the forced vital capacity, other words known as FVC. So the FEV1 is the total amount of air that we can expire in 1 second. So we'll just mark 1 second on our time axis here. So the FEV1 point would be this point right here, and we'll just assign an arbitrary value here for the FEV1 as 2.8. And although these values that we're going to be using reflect normal values, you don't have to memorize any of the values for this video. However, there will be some ratios and percentages that you will need to know, and I'll point them out as we move along. So to confirm that the FEV1 is in fact 2.8 liters, we would draw a line to the x-axis to mark that we're at time point 1 second, and then we would draw a line to the y-axis and see that it is indeed 2.8 liters. The next point that you want to pay attention to is the forced vital capacity, or the FVC. It is the total air that you can expire over your entire breath. So it's going to be the end point of the graph. So we'll put this point in on the end of the curve right over here, and we'll assign the FVC to be a value of 3.5 liters. And again, you would draw a line to the x-axis and a line to the y-axis and confirm that this is indeed 3.5 liters. And the most important part of the FEV1 and the FVC is to take the ratio between them, and that ratio is called the FEV1 FVC ratio. The value that this ratio produces is a predictor of pulmonary function. And so for the case of the normal values that we have up on the screen here, we would be taking the ratio of FEV1 to FVC. So in this case, it would be 2.8 divided by 3.5, which would give us a value of 0.8 or 80%. And this actually is the value for normal healthy lungs. The FEV1 FVC ratio for normal healthy lungs will give you a value of about 0.8 or 80%. So I would keep 0.8 in the back of your mind as a value to remember. All right, so now we're going to add in our obstructive lung disease curve here. And one of the main takeaways for the obstructive lung disease curve is that the FEV1 is severely decreased in obstructive lung disease. And that's because right off the bat, they're exhaling against some sort of obstruction, whether it be a foreign object or it's because of collapsed airways. But right away, there's really high airway resistance, and so the curve is shifted upwards. So if we just add in our FEV1 here, we would see that at 1 second, they're exhaling significantly less than a normal individual would. And furthermore, for the forced vital capacity, it is also usually decreased in obstructive lung disease, and that's because they just can't breathe as much air out over time, and also remember they have a very large residual volume, and so they breathe out their vital capacity, and they start to hit that residual volume fairly early. So we'll just put in our FVC point at the end of the curve here. And when we're thinking about the FEV1 to FVC ratio for obstructive lung disease, we just draw in the ratio here, FEV1 over FVC. Like we said, the main takeaway is that FEV1 is going to be severely decreased as they have a lot of resistance right off the bat. And the FVC is also going to be decreased, but it won't be decreased as much as the FEV1 is going to be. And because the numerator is decreasing more than the denominator, the entire ratio is actually decreasing. So we'll just put in our ratio here. We can see that it's going to be less than 80%. So the value that you should really be keeping in your mind is the fact that it's less than normal. It's less than 80%. And now we'll put in our restrictive lung disease curve here. And you can actually see that the first portion of the restrictive lung disease curve is very steep. They actually initially exhale more air than the normal person. And the reason for this is, remember, it's really hard to expand the lungs in restrictive lung disease. And so the person will be using a lot of musculature to try to keep the lungs open. And as a result, it's really going to be pulling on that pleural space and generate a lot of negative pressure, which is going to translate to the lung parenchyma really pulling on the airways and really keeping the airways wide open. And when the airways are wide open, there's going to be very low airway resistance, and so airflow is going to be very fast at the beginning of the expiration. However, recall that in restrictive lung disease, they breathe at very low lung volumes. So very quickly, this curve is going to taper off as they start to exhale almost all of their lung volume. And so depending on how fast the curve tapers off, the FEV1 actually might be normal, or it's going to be slightly decreased in restrictive lung disease. So we'll just add in our FEV1 point here. We can see it's fairly close to normal, maybe slightly decreased. However, the main takeaway for restrictive lung disease patients is that maybe they'll have slightly decreased FEV1, however, their FVC, or their forced vital capacity, is definitely going to be decreased. And that's because they can't really blow out that much air over their entire breath because they don't have that much air to begin with. So maybe these patients will blow out air fairly quickly, however, the curve is going to very quickly as well taper off because they're blowing out almost all of their lung volume down to the residual volume. So we'll just add in our FVC point here. And we can see that the FVC of a restrictive lung disease patient compared to normal is significantly decreased, whereas the FEV1 of a restrictive lung disease patient is not as decreased compared to normal. And so when we think about our FEV1 to FVC ratio, we'll just draw it in here, FEV1 to FVC, the FEV1 is only slightly decreased, whereas the FVC is very or definitely decreased. And so because the denominator is actually decreasing more than the numerator, this ratio can actually be elevated. And so we say that the FEV1 to FVC ratio is usually greater than 80%, however, it can also be 80% as well. So in restrictive lung disease, the ratio is going to be normal or greater. So just to summarize here, in obstructive lung diseases, the FEV1 is going to be severely decreased, and the FVC is going to be decreased, but not as much. And so for the FEV1 FVC ratio, because the numerator is decreasing more than the denominator, the total ratio is going to be decreased. And for restrictive lung disease patients, the FEV1 is going to be slightly decreased, and the FVC is definitely going to be decreased because remember, they can't breathe out that much air over their entire breath because they don't have that much lung volume to begin with, and because the denominator is falling to a greater degree than the numerator is, the ratio could be elevated in restrictive lung disease. However, if the FEV1 and FVC are falling to a similar degree, then the FEV1 FVC ratio could also be normal in a restrictive lung disease. Alright, and that's all we got for our video on pulmonary function testing, and join us for our next chapter when we go over respiratory physiology and blood.